One great application of differential equations is what we call the tank model, or the bathtub analogy that we might have seen before, where something flows into some sort of tank. It could be a cistern, it could be a bucket, it could be a barrel, it could be some sort of mixing tank, and potentially there's water flowing out. Now, what we're always going to assume is that there's something, that the water coming in is concentrated with some sort of substance, and maybe that's salt or sugar or some sort of chemical, chlorine, and then as that water flows in, it starts to, I'll just use the word pollute this water inside that we have here. And what we're going to assume in order to be able to model how much of that substance is inside of there, because keep in mind, this water could initially be clean completely. And so as you start pouring contaminated water in, we're going to assume that this water instantly becomes well mixed. Now, essentially, we're assuming that there's kind of like a propeller in here, and that propeller that paddle is spinning and constantly stirring everything up. This just makes it really easy to model, because if we just assume that, you know, the substance just kind of lies here on the top, well, then we don't have a very good model, because we can never assume that what is inside is what's coming out. So as this becomes well mixed equally, all of these, you know, chemical particles are well mixed in here, then that water is also pouring out, and meaning that immediately you start getting some of that substance exiting. But because there is polluted water coming in, polluted water going out, the concentration of that substance inside of here is going to be changing over time. So it's hard to actually write a model that is not a rate of change model. However, if we first of all start off with assuming we have water coming into a tank, and usually it's going to be some units of volume per units of time. Now this could be something like you have gallons per minute, you could have gallons per hour. There are lots of different units of volume that we could use. We could use liters per second. It just really depends on the context. And we're going to say it's concentrated with some substance. Okay, that's going to be units of the substance divided by units of volume. So basically how much mass there is of a substance distributed evenly in that tank. This could be in grams per gallon, or it could be in pounds per liter, right? So these are all kind of units of some sort of mass. We assume the tank is well mixed at all times. For model simplicity, as we've said, we're not going to assume that the substance just kind of pools right at the top. We're going to assume it's immediately well mixed inside of the tank. Okay. Now we're going to define our dependent variable to be the amount of substance in the tank after t units of time. Okay, so that's actually how many, let's say the amount of the substance is in grams, and the unit of time we'll just say is in minutes. So when we build a model, dy dt, this will have units of grams per minute. Which begs the question, okay, so if we have units of volume and we have units of concentration, then what do we do to get, here we have gallons per minute, what we want is grams per minute. Well, for example, if our volume coming in is in gallons per minute, we can call this flow rate. And then here we have the concentration. And let's say our units of substance of mass is grams and volume is gallons. Well, if you know how many grams are coming into each gallon, and you know how many gallons are coming in each minute, well, multiplying how many grams there are in each gallon by how many gallons you have will give you the total number of grams in each unit of time, in each minute. So we can multiply those together. Units of volume divided by units of time times units of substance mass divided by units of volume. So notice that the units of volume actually cancel out, and you're left with units of substance mass. Okay, that could be in, like we said here, grams, divided by units of time, which we could say is in, maybe minutes. So when we multiply these together, we get the proper units that we want. Now this is what is coming in. This is what is coming into the tank. And then we're going to subtract away what is going out, right? So it's sort of like if you're filling up your tub at, let's say, 20 gallons per minute, and you're draining at a rate of, let's say 12 gallons per minute, well, that means your tub is filling up at a rate of 8 gallons every minute, right? Because you put in 20, you only take out 12, means you're getting 8 more than you had in the previous minute. So again, here in the rate out, units of volume cancel out. Again, we get units of substance mass divided by units of time, and this is out of tank. So in red, here's what we have coming out, right? This is what's coming out. And then over here, we have what's coming in. Perfect. So that's pretty much what it boils down to. We just now have to figure out what these quantities are. There are 4 things that we need to build values for: the units of volume, the flow rate in, the concentration in, the flow rate out, and the concentration out. All right, let's get an example. Suppose water flows into a tank at 30 gallons per minute, concentrated with 8 grams per gallon of sugar. Okay, so here we have whatever kind of tank we want to draw. And I just like to draw a generic box because I'm not an artist. And so here we have 30 gallons per minute, 30 gallons for every 1 minute. Okay, I like to write my units this way. That way, even though it's 1 in the denominator, I don't like to write 30 gallons/minutes because this helps me keep track of a proportion. And I also have 8 grams per gallon of sugar coming in. So it should be 8 grams of sugar per gallon, make more sense. Okay, and so now what we see here is that if there's 3 gallons in every minute and there's 8 grams in every gallon, well, that's going to mean there's 24 grams coming in each minute. We multiply these quantities, our gallons cancel, and now you can see we have 24 grams per 1 minute. Now the reason is because, remember, Y is going to be defined as the amount of the substance, which is sugar, measured in grams in the tank after, well, our unit of time seems to be in minutes here because that's how it's mentioned. We could always convert to hours if we wanted to, but why would we go through that? And now, so what's coming in here, right? This is coming in here. It's filling up. There's water in here, and well, excuse me, I left out a detail here. Let's say that the tank is currently full. It has 50 gallons of water in it. So we do need that tidbit as well. You'll see in a moment why that's going to be important. So we have 50 gallons in there. Now, because the water flows out at the same rate, in other words, 30 gallons per minute, we know that the water level won't change. We know that it is full with 50 gallons of water, but because we're pushing out as much as we're pushing in, the volume is not going to change. So here what we have to do now is we need our units of volume per units of time. So this is where we need that. This should be, 30 gallons back here. So this should be 240 grams, excuse me, sorry about that. And so we have 30 gallons per 1 minute coming out, multiplied by how many grams there are inside of each of these 50 gallons. Okay, so that's our volume. That's where we needed that. That's our volume inside the tank, units of volume. Now keep in mind that what's coming in is only concentrated per gallon, but what is coming out is dependent upon how much volume there is in here, because remember that all of those grams that come in are going to be equally mixed within that 50 gallons. So we have to take the number of grams that we have in that 50 gallons and divide it by the 50 gallons. Well, how much we have in here is actually unknown at the moment because keep in mind, again, as we mentioned earlier, water flowing in, water flowing out. And now the amount of sugar that is actually inside of that tank is specifically what our variable defines. Y is the amount of sugar in the tank. Okay, so how many grams do we have inside the tank? Well, we have Y grams. Y grams. That's the only difference between the output and the input of this tank is the output. That's where our unknown variable comes into play because simply put, if we already knew how many grams were inside that are there at any given moment, we wouldn't need to build a differential equation to model the rate of change. We would be able to already tell ourselves how many grams there are. So once again, keep in mind, we can't say that there are, there are 240 grams in here after 1 minute, because although 240 grams make their way in, because they are instantly well mixed in here, some of those 240 grams exit at the same time. So yeah, it's not quite as easy as multiplying 240 grams by the number of minutes that have passed because of the outflow as well. Well, now let's put it together. Simple as dy dt equals the number of grams per minute coming in, which is the 240 grams per 1 minute, minus the number of grams of sugar coming out. Well, again, notice our units here, although they involve a variable, the gallons cancel out. We have 30 times y grams divided by 50 gallons. I'm sorry, 1 minute times 50 is 50, and that is in units of minutes. So you could simplify this a little bit, and usually we're not going to write in the units. I'm just putting them there so you could see them. This would be 240 minus 30 over 5 is 0.6. Sorry, 30 over 50 is 0.6 times y. And our initial condition, y of 0, number of grams present of sugar inside of there at time 0, well, it's initially clean water and free of sugar, so y of 0 is equal to 0. This is a separable ODE. We could solve this and we could answer questions about how many grams there are actually in there. And that is the extent to which we're going to take this. Now, the beauty of this model is that this sort of concept of rate in minus rate out is applicable even if the rates are not constant. So let's change things up a little bit. Suppose water flows into a tank at 2t gallons per minute. Okay, what that means is that the number of gallons per minute that we have coming in, I'll write this as a little quick t table, the number of gallons per minute in is a function of time. So at time 0, 2 times 0 is 0, and there's nothing flowing in at that moment. But at time 1, 2 times 1 is, you have 2 gallons per minute coming in. At time 2, 2 times 2 is 4 gallons per minute coming in. And so the idea here is that we're kind of opening the faucet more and more and more kind of linearly as time passes by and letting in water at a faster rate. Okay, keep in mind that time is continuous, so there is stuff happening between 0 and 1 minute, but I just wanted to point out that, hey, look, the rate of change is constant and the volume of water coming in every minute changes. And we'll also say that the concentration changes. It's going to change at e to the negative t grams per gallon of sugar. Now, once again, what we can do is we can build a table, but I'm going to do a little graph here, and as a function of time, the number of grams per gallon is going to be exponentially decaying, meaning that your concentration isn't always the same, that maybe there's like water runoff off the side of a mountain, and so we're kind of, some of the water, initially a lot of that chemical gets leached off the mountain, but as time passes, there's less and less of it. And so we could say that maybe the concentration of, in this case, sugar, is getting smaller and smaller as time passes. So everything, concentration and flow rate, is time-based. Now, water flows out at a rate of 0.8 t gallons per minute, assuming the water is initially clean and free of sugar. Write an ODE model with initial condition for this scenario. Okay, again, notice that the water is flowing out at a slower rate, although variable, than it is coming in. So if I build my box model here, I can pretty much label it the same way. I have coming in 2t gallons per 1 minute multiplied by the concentration, which is e to the negative t grams per 1 gallon. Okay, gallons cancel out again. My rate in will be this function 2t times e to the negative t grams per minute. So let me just write that already. dy dt equals 2t e to the negative t. Okay, that's going to be grams per gallon. I'm not going to write the units, but I'm sorry, grams per minute, minus what's coming out. Now, here's where we have to be careful. Because our volume in is 2t gallons per minute, and our output is 0.8t gallons per minute. Okay, so I still have coming out a unit of gallons per 1 minute. But now what I need to do is I need to multiply by the concentration in grams over gallons. Okay, that way I get grams per minute minus grams per minute in my dy dt. Well, again, what's inside of here is once again our variable. Same definition as above. At any given moment inside of here, we have y grams. Okay, so we have y grams inside of here. Now, initially, the tank initially has 50 gallons of water. So we have 50 gallons in here. So at the start, we have 50 gallons, but keep in mind that the volume is actually changing. It's not always 50 gallons because in 1 minute, you have 2t gallons coming in and 0.8t gallons per minute coming out. So let's do this. First of all, the difference in the change in volume per change in time is equal to 2t in minus 0.8t out. Okay, this is in gallons per 1 minute. So what this means is that I have a net change of 1.2t gallons per 1 minute. Okay, that means my tank is actually filling up, right? It's positive. The tank is filling up at a rate of 1.2t gallons per minute. But I can't add that to the 50 because of the fact that this is a unit of gallons per minute. Now over here I've written, if water flows in at a different rate than it flows out, we must add up the difference between what goes in and what goes out. In other words, the total volume in the tank after t units of time is this v of t function. Now that's added to the 50, of course, because this is just going to give us the total change in volume, or the total change in volume. So I think we should probably say plus v v0, v initial, which is in this case our 50. Okay, so let me actually take this 1.2t, and we're going to add up the gallons per minute for all of the minutes combined. This comes out to 0.6t squared, right? And then you'd normally have a plus c on here. And I guess that we don't really need the plus v naught if we just remember to write the plus c. Initially at time 0, we have 50 gallons. So if this is your v of t, is 0.6t squared plus c. And now you have 50 gallons at time 0. You get c is equal to 50, and your v of t function, your total volume is 50 plus 0.6t squared. So that's our denominator. So now we need to take that guy, and we're done. Take this guy and insert it here so that our differential equation now becomes 0.8t times y, okay, that's this product here, divided by 1 times our function 50 plus 0.6t squared. That is now in, notice, grams divided by minutes. We have grams per minute in minus grams per minute out. And boy, this looks like a complicated differential equation to solve. Again, y of 0 equals 0. There's our model. Now, keep in mind that this can only hold 100 gallons of water. So this tells us something about our domain, that essentially we would need to know when this denominator, this total volume, becomes as high as 100. That means the tank is full and it can't fill up anymore.